We're now going to start forces. Forces are going to be a fairly large unit. We're going to spend pretty much until the end of the year in terms of December working on forces, and then they're going to keep popping up throughout the year, but the main chunk of forces will take us about 2 months. So, introduction to forces. Let's begin with what a force is, and then we're going to define certain types of forces, and then finally get to force diagrams. A force is an interaction between two objects. It's also a push or a pull. So any object is going to have some kind of interaction with any other object, so we've all got forces acting on us all the time. The symbol for force is a capital F, and the unit for force is the Newton. And the symbol for Newton is a capital N. Forces are everywhere, so what we're going to do is define the main types of forces that we'll be dealing with. I'll give examples of each of those, and then we're going to look at Newton's first law. Our first type of force is a normal force, and a normal force is a force that is perpendicular to a surface. Normal just means perpendicular, so it's at a 90-degree angle to whatever your surface is. The symbol for a normal force is a capital F with a subscript of N, and it's a capital N. And an example of a normal force, so if you've got a book, this is a book, lying on a table, you're going to have a normal force pointing directly up. So making a 90-degree angle with whatever your surface is, in this case the surface. In this case the surface is the table. If you have a wall, and say you've got a picture on a wall, perpendicular to that surface would be pointing directly outward. So the normal force would be that way, and in this case the normal force was up. So whatever direction your surface is, a normal force will always be perpendicular to that surface. Next we have a frictional force. A frictional force is going to be parallel to a surface. It's always going to oppose the direction of motion or the direction of the intended motion. So in other words, if something is at rest and on an angle, friction would oppose the direction that that object would slide if it were moving. The symbol for frictional force is a capital F with a subscript of capital F, and an example would be a book sliding across the table. So here's our table, here's our book, and it's now moving across the table. Frictional force is parallel to your surface, so it's going to point to the left because it's opposing the direction of motion. So going to the left would be a frictional force. If your object is not moving, so this is usually going to happen if you're on an angle. So say our surface is on an angle and we've got a book that's not moving on this angle. The book wants to slide down the incline, but let's say this is at rest. The book wants to slide down the incline, but friction is keeping that from happening because it's opposing the direction of intended motion. So if the book wants to slide down, you're going to have a frictional force parallel to the surface sliding up. And this would also work if you have, let's say you have a table on the floor and you're pushing on the table but it's not moving, so this table is still at rest. If you're pushing with a force to the right, you're going to have friction going to the left, keeping the table from moving. So this is what I mean by the direction of intended motion if the object is at rest. If the object is moving, then friction's always going the opposite way. Our next type of force is a tension force. This is going to be due to a string, rope, chain, cord, any kind of rope, or anything that falls in that general category. The symbol for tension force is a capital F with a subscript of capital T. An example would be keys hanging from a lanyard. I think tension forces are always the easiest ones to identify, especially if you're given a diagram, because the tension is whatever direction that object is. So in terms of objects, string, rope, chain, cord, whatever direction that is, that's what way your tension force goes. So if we've got keys hanging from a lanyard, your tension force would be right along the lines of the lanyard. So that would be Ft, that would be Ft. Say you have a ceiling and we've got a box suspended from a ceiling, so the tension is pulling the box up. Your tension force goes directly up. So whatever direction your string, rope, chain, cord, etc. is going in your diagram, that's the direction of the tension force. And again, I always think that's the easiest one to identify because it can't really be anything else. It's definitely not normal, it's definitely not friction, it's tension. Our next type of force is a more general force, contact force. So this is what you're going to use if it's not normal, tension, or frictional force. And a contact force is any force resulting from two objects being in direct contact with each other. So they have to be touching. The symbol for contact force is F with a subscript of C. So this is just going to be any general force that has no other name for it. So again, if it's not tension, normal, or frictional, it'll probably be a contact force. It's possible to have multiple contact forces on the same object. You would just call them FC1, FC2, etc. Example of a contact force, if you've got a box being pushed across the floor, a hand pushing that box, causing it to move, would be exerting a contact force in the direction that it was pushing. So a contact force is always going to be whatever direction it's being pushed or pulled. And again, it's just a very general term when there's no other word for the types of forces. Our last type of force is a gravitational force. And this is the force that results because of Earth's pull on an object. So every single object on Earth is going to experience a gravitational force because Earth is pulling down on the object. It's a long-range force, which means that the two objects are not in direct contact. So the gravitational force is not a contact force. It's because of it's because of a gravitational interaction as opposed to a direct interaction. And the symbol for gravitational force is F with a little g for the subscript. And this matters. It's little g, not a big G. Every single gravitational force will always point down if you're being pulled by the Earth. So Earth always pulls down because gravity points down. So all gravitational forces, because of Earth or the moon or whatever planet you're on, are going to point down if you're pulling on them. So these are the main types of forces that we'll be dealing with. So make sure you know what they are. Make sure you're able to identify what direction a certain force will go based on what the definition of that force is, and we'll be doing plenty of practice with this. What I'm going to do now is show you how to draw a force diagram. But before we do the force diagrams, I do need to define one more thing, and that's Newton's first law of motion. Okay, Newton's first law of motion tells us that an object in motion will stay in motion at a constant speed, and an object in rest will stay at rest unless an unbalanced force acts on the object. So this is also known as the law of inertia. I'm going to define what inertia is in a minute. Inertia is in a minute. And pretty much what Newton's first law of motion tells us is that forces must always be balanced if there is no acceleration. So in other words, the amount of upward force has to equal the amount of downward force. The amount of force to the right has to equal the amount of force to a left. That doesn't mean that your object is not moving. It just means that it's either not moving or moving at constant speed or velocity. So what is inertia? Inertia is the tendency of an object to resist change. So objects want to keep on doing what they're already doing. If they're moving, they want to keep on moving. If they're at rest, they want to stay at rest. The more mass an object has, the more inertia it has. So inertia is directly related to mass. Think of it this way. If a boulder, a giant boulder, is rolling down a hill, it wants to keep on moving, so it's going to be really hard for you to stop that boulder if it's already rolling. Same idea, if the big boulder is at rest, it's going to be really hard to get that boulder to start moving. If you're dealing with a little rock rolling down a hill, a rock is a lot less massive than a boulder, so it's going to be easier and have less inertia if it has less mass. It'll be easier to stop a rock if it's rolling down a hill. It'll be easier to get a rock to start moving if it's already at rest. So Newton's first law of motion is also known as the law of inertia because it pretty much tells us that objects want to keep on doing what they're already doing. The main idea and what we're going to be dealing with over the next couple of weeks is that forces need to be balanced if there is no acceleration. And again, no acceleration means either the object is not moving or it's moving at constant velocity. So keeping Newton's first law of motion in mind, let's look now at how to draw force diagrams with balanced forces. Force diagrams are fairly straightforward. What they're going to do is show all the forces acting on an object. You might also see them sometimes called free body diagrams. I'm just going to call them force diagrams, but a force diagram or a free body diagram are the same thing. So to make a force diagram, let's say that we're going to draw a force diagram for a pretty simple example. Let's do a book being pushed across the table. So it's moving and it's being pushed by a hand. That's a really bad hand. But hand pushing the book and it's moving. You're going to start with a dot to represent your object. So my object in this case that I'm looking at is the book. Here's the book being represented. You're going to draw an arrow for every force in the direction that the force is acting. So it's on Earth. We know that there's going to be a gravitational force pointing directly down. Again, gravitational force always goes down if it's the Earth pulling on the object. Next you have your surface, which is the table. Your surface pushes up on the book. So going up, we're going to have a normal force. You have your hand pushing the book to the right. So to the right is going to be a contact force. And let's assume this is moving at constant speed. Constant speed means no acceleration, so your forces need to be balanced. So going to the left will be a frictional force parallel to the motion. And that's how you would draw the force diagram for a book being pushed across the table at constant speed. Let's now say you want to draw a force diagram for, I don't know, let's do a lanyard with the keys. So we already looked at that example when we defined a tension force. This is a lanyard with keys, and we'll say it's at rest. We want to draw the force diagram for the keys. So identifying our object, representing it with a dot. We know that there's a gravitational force going directly down. Gravity always pulls objects down from Earth. We've got two tension forces, one going up and to the right, I'll call that FT1, and one going up and to the left, we'll call that FT2. Newton's first law of motion tells us that forces need to be balanced. So that means that forces need to be balanced in the y direction as well as the x direction. We can't really say that this diagram is balanced because we have these two forces that are off to angles. We're not going to show you how to balance this yet, but just know that this is how you would draw the basic force diagram for a lanyard at rest, or in other words, keys being held by a lanyard at rest. And let's just do one more example. Let's say this is for something that is on an angle and at rest. So book at rest on an angled table. And we want to draw the force diagram for the book. Our surface is going to be at an angle. Gravity always goes directly down. So this would be Fg. By definition, a normal force is perpendicular to the surface. So normal force goes up and to the left because that's 90-degree angle with my surface. Book wants to slide down the table, so frictional force opposes that intended motion and goes up the table. Again, this is not a balanced force diagram because we have a force at an angle. This one right here, not in line with the x or the y axis, but in a few days we'll talk about how to balance out a diagram like this. So force diagrams, I think, are fairly straightforward. You're just drawing the direction of the forces. These will become slightly but not really much more complicated when we start breaking forces apart into their components to balance them out if they're not accelerating.